In this lesson, we're going to talk about Pascal's triangle, which gives you an easy way to compute the coefficients whenever you expand a polynomial, or an easy way to compute combinations. So these first 2 points here give a description of how to compute Pascal's triangle in words, but I think it's easier just to see from the triangle. Although, just to see them real fast, row 0 has a 1 in the triangle, and then for each row that follows, the row is going to branch to the right and the left, and whenever two numbers collide, they're added together. So let's see what this looks like. Row 0 starts with a 1, as it says. Then, to get row 1, you take row 0 and branch it. So it goes to the right, it goes to the left. So there's two 1s in row 1. Now for row 2, we're going to branch row 1 to the right and the left. So it branches this way. So this one will branch left and give us a 1, but this one, when it branches right, will collide whenever this one branches left. So we get two 1s colliding together, which gives us a 2. And this one will branch right, which gives us a 1. And then we continue this on down. So this 2 will branch left, this 1 will branch right, and they collide and give us 3. And this 1 will branch right to give us a 1. This one will branch left, and the 2 will branch right, and that makes 3. So you continue that pattern on down the triangle, each one of these numbers. So like this 10, for example, is caused by a collision of the 4 and the 6. So 4 plus 6 equals 10. And it turns out that that triangle is not so hard to generate, but the values on the row n are actually n choose 0, n choose 1, n choose 2, up to n choose n. So that's the claim. We're going to show that in a second, but let's look at an example. So if I take row 4, for example, this is 1, 4, 6, 4, 1, and that's 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. So this actually computes 4 to choose k for any k between 0 and 4. We will show that this result is true by induction. So for the base case, row 0 is 1, which is 0 choose 0, because 0 factorial is 1, and so 0 factorial over 0 factorial 0 factorial is just 1. And the second row is 1, 1, which is 1 choose 0 and 1 choose 1, because they're also both 1. So now let's do the inductive step. And so we're going to suppose the claim is true for row n. And the interesting part to look at really is we want to show it's true for row n plus 1, and we got to check this is true for n choose k, where k is between 2 and n. So on the endpoints, we have n plus 1 choose 0 is 1, and n plus 1 choose n plus 1 is 1. That's always the case, and we always have 1s at the end. So those are accurate. But what about whenever we have n choose k for some k between 2 and n? Well, we're going to get a collision of two numbers from row n, and those two numbers are going to be n choose k minus 1 and n choose k. So we have this row up here, with n choose something, and there's an n choose k minus 1, n choose k minus 2, n choose k minus, this should be n choose k plus 1, so it goes up as you go across, and so on. And then in the next row, we're going to have an n plus 1 choose k is going to be the collision between n choose k minus 1 and n choose k. So when these two collide, well, at least the claim is saying that. So question mark, is this actually equal to n plus 1 choose k? And what is going to be in the triangle is the sum of these two numbers. So we'll have n choose k minus 1 and n choose k added together, which is n factorial over k minus 1 factorial times n minus k plus 1 factorial, plus n factorial over k factorial times n minus k factorial. And there's not really anything tricky about this. You get a common denominator. So on the left side, we need to multiply by k over k, and on the right side, we need to multiply by n minus k plus 1 over n minus k plus 1. And that gets us a common denominator here of a k factorial times n minus k plus 1 factorial. So we can combine those together, and on the top we have n factorial in both terms. So we pull out the n factorial, and we'll get a k plus n minus k plus 1. So this is just the combination of this k and this n minus k plus 1. Now the k and the minus k are going to cancel. So this is just n factorial times n plus 1 all over k factorial times n minus k plus 1 factorial. And let's see if I can get myself out of the way in a good position. N factorial times n plus 1 is n plus 1 factorial, right? Because this is the product 1, 2, 3 up to n, and then we're also multiplying by n plus 1. And by definition, that's n plus 1 choose k, because it's n plus 1 factorial divided by k factorial times n plus 1 minus k factorial. So that is the result that we wanted, and therefore the claim must be true for every position in row n plus 1, and thus is true for row n plus 1. So I show the example here with 4 once again.